Thank you, and thanks for coming back. So the plan for this remaining hour is I'd like to give some idea on how the infinitesimal decomposition of the tangent bundle can be shown. And then I would like to start off in a somewhat different direction, introducing another set of methods that can be used to study the minimal models of varieties with a Kodara dimension 0. But first things first, so let me start with this is now 5, I guess. So a decomposition idea of proof. And because the theorem is no longer in the blackboard, let me recall what the setup was. So the setup is this X, a projective variety, with KLT singularities. We assume that the canonical divisor is numerically equivalent to 0, and we want to show find a cover x twiddle of x, so a quasi-étal, so such that x twiddle is of the form an abelian variety times some z, and the tangent sheaf of that z should admit the decomposition. This is where we are headed, and I'd like to decompose the proof or its sketch into 3 steps. So step 1 is, in a sense, not really ours. It refers to results of Kawamata from the 1980s, where he essentially did part of the job for us. So his contribution is a splitting of the abelian part in our setting. So Kawamata has shown if H1 x OX is positive, then after quasi-étal covering, an abelian variety will split off. So then abelian variety splits off. And this is essentially his study of the Albanese morphism in the presence of rational singularities. He essentially shows that the Albanese map is much more than just a map. It's an étal trivial fiber bundle with these assumptions here. So as a result, or as a consequence of this, assuming that I can split off, or that I split off as many abelian varieties as there are, I can always assume that H1, the irregularity, is 0, and it stays 0 if I pass to further quasi-étal covers. If it's non-zero on a quasi-étal cover, a split of another torus dimension goes down. Eventually, that better has to stop. So, so I can thus assume that the irregularity H1 XOX is 0 even on all quasi-étal covers. And this is extremely useful. Not only have I split off any abelian variety, but that the irregularity is 0, that also means that my Picard group is discrete, and in particular, any Q Cartier divisor that is numerically trivial will actually be torsion. So given a Q Cartier divisor numerically trivial, a multiple of this will be linearly equivalent to 0. So there exists a covering, a quasi-étal covering, such that the pullback becomes 0. So in particular, any numerically trivial Q Cartier divisor is torsion and becomes trivial after quasi-étale covers. So that means whenever in the remainder of the proof I encounter a divisor that's numerically trivial, I will say, oh, we go to a quasi-étale cover and assume from now on that it's actually linearly equivalent to 0. One specific case is obviously the canonical divisor. So we can assume now that the canonical divisor is a Cartier and trivial. So in particular, I can assume that Kx is linearly equivalent to 0. So this is a resume of the work of Kawamata. And now I would like to continue with the ideas of Bogomolov. And Bogomolov's idea, central idea, maybe can be formulated like this. We'd like to decompose a tangent sheaf. Or if you wish, we'd like to decompose the dual of the tangent sheaf, the sheaf of reflexive differentials. I don't know how to do this, but if such a decomposition exists, that also gives me a decomposition on the ring of differential forms. So what he's looking for to start is not immediately a decomposition of Tz, but he wants to look at some duality that exists in the ring of differential forms. So what he really wants to say is Kx is linearly equivalent to 0, means there is a unique up to multiple top form that nowhere vanishes. That, let's call that sigma. And what he wants to say is instead of decomposing Tz right away, let's prove the following. So if you give me a P form, then there always exists a complementary n minus P form such that the two together wedge to give me the unique top form that I have. This is what we want to do. And for this, we need to understand the action of our forms on cohomology. This is a bigger diagram, so I better prepare and get my right. So Bogomolov's idea is want to show given any P form, say alpha, there exists an n minus P form. Oh, I should say a reflexive form. Reflexive n minus P form beta such that alpha wedge beta is the nowhere vanishing section, say sigma in H naught x kx, which is isomorphic to C. Right. And for that, I would like to understand the action on cohomology. So I recall, if you wish, the extension result, or here is really the definition of canonical singularities, that this form sigma has a lift as an honest differential form. This is a section in the Grothendieck pre-dualizing sheaf, but it has a lift as an honest differential form to any resolution of singularities. So if pi from x twiddle to x is a resolution, then So sigma lifts to a top form, say tau in h naught x twiddle k x twiddle. And now here comes the diagram that I want to discuss. So, and the following diagram plays a role. I start with HQX OX. I can multiply with the form sigma. OX is isomorphic to omega x, and the isomorphism is given by multiplication with sigma. So this is HQ omega x or kx, and this is an isomorphism. And I also I can do that upstairs. I have HQ x twiddle, OX twiddle. I have multiplication with tau, and that goes to HQ x twiddle, omega x twiddle. Or I could also write this as Dolbeau cohomology groups on the manifold. That makes no difference. So this is H0Q x twiddle and H NQ x twiddle. So multiplication with tau. And here I have the Dolbeau isomorphisms. However, there's more. One thing that we know for a fact, there are many proofs in the literature, is that the singularities of the minimal model program, the KLT spaces, they have rational singularities. So that means I have an isomorphism here. So this is rational singularities. On the other hand, we have the Grauert-Riemenschneider vanishing result that I started with in the first talk today, and that gives me an isomorphism here. So this is Grauert-Riemenschneider, and I hope you will find it plausible without further ado that this forms a commutative diagram. So in particular, what I want to say is that the action of multiplication with tau on Dolbeau cohomology is an isomorphism. So the following diagram commutes. So multiplication with tau is an isomorphism, which is maybe not 100% clear from the outset, because tau is the lift of the reflexive form sigma that we have, but on a resolution of singularities, tau will usually have zeros. I mean, this is how the discrepancy comes about. So we are multiplying here with a form that does have zeros, and yet we see that the action that we get on cohomology is isomorphic. And this is crucial, because now comes this duality thing that we have in the ring of differential forms. So using this, I can write down a long list of identifications that eventually turn our problem into a well-known statement that is Serre duality. So, so use this. I identify what do we have? H naught omega p dual x, where H naught omega n minus p dual x. So this is the same as differential forms that are defined only on the smooth locus omega p x reg tensor H naught omega n minus p x reg. I know by the extension result that we started with in the morning that any reflexive form or a form defined on x reg downstairs gives me an honest differential form upstairs. So this is the same as H naught omega p x twiddle times H naught omega n minus p x twiddle, or I can write this as Dolbeau cohomology groups. So HP naught x twiddle times Hn minus P naught x twiddle. Now I can conjugate in the second summand. So this is complex conjugation HP naught x twiddle times H naught n minus P x twiddle. And I can multiply here with tau. So this is conjugation. Now we have multiplication with tau in the second factor, which we have seen is an isomorphism, so nothing happens. So that will then go to HP naught x twiddle times Hn, n minus P, x twiddle. I conjugate again. Then I go to HP naught x twiddle times Hn minus P. This is n minus P comma n x twiddle. And then I have the Serre duality morphism, which is non-degenerate. So this is Serre duality. Voila. And Serre duality is non-degenerate. So we have a morphism from, if you wish, here or here or here to C, which is non-degenerate. And what is that morphism really? If I write it down, say from here to here, then if I have a form alpha, I have a form beta, and that gets mapped to the integral of, well, I conjugated beta, I wedged with tau, I conjugated back, so by the end of the day, up to sine, this will be this. And this map is non-degenerate. So in particular, if there is an alpha, there must be a beta. If you give me an alpha, then there must be a beta such that the number 1 comes out. So in particular, there is a beta, such that alpha wedge beta is non-zero because I take the integral and then 1 comes out. So there is a beta such that alpha wedge beta gives me a not identically vanishing top form, but there is only 1. So this is non-degenerate. So we conclude. As I mentioned in the beginning, given alpha, I think I wrote down the statement already. So let me just say conclude. Well, step 2. So we have seen that there's some structure in the ring of differential forms. There's some sort of duality there. And then step 3. We can turn this into a statement about the tangent sheaf. Now, how do I do this? So one case is obviously the tangent sheaf is stable, and it remains stable whatever I do to it. Then I can say, great, I'm finished. I have only one summand. And the proof is finished. So let's assume Tx, or equivalently omega px. I keep writing these double duals, but I'm getting tired, so let me use a shorthand notation. Square brackets means double dual. Or equivalently, this is not stable, perhaps after taking a quasi-étale cover. Well, then I have a destabilizing subsheaf. So then have destabilizing, say, A lives inside of Tx, and that has a quotient, say Q. So then I have a destabilizing A. Right. So what is the slope of A? I claim that the slope of A cannot be positive. For if it was positive, well, Tx, the slope of Tx we know. This is the Chern class of Tx is precisely the canonical, the numerical class of the canonical bundle, which is trivial. So if there's something positive in there, the quotient would be negative. But if the quotient is negative, then that means I have a negative, sorry, I want to write omega. I want to write omega 1x here. If the quotient is positive, then Miyaoka has shown, and that was featured in George's talk this morning, that I have a negative quotient of omega 1, so equivalently I have a positive subsheaf of Tx, and that means my space is covered by rational curves. But we are now discussing a canonical variety. Pardon? B. Sorry. Let me, you're right. Right, so if the slope of A was positive, that means I find many rational curves. But spaces with canonical spaces with Kodaira dimension 0, they're not covered by rational curves. So now, if yeah. Yes. So if slope of A is strictly negative, then Miyaoka says X covered by rational curves. And this is a contradiction to the Kodaira dimension. So the slope of A will be equal to 0. And that is true no matter what polarization I use to define the word slope or stability. This is true for any polarization. And if you have a sheaf whose slope is 0 with respect to any polarization, there's only one way this can happen, namely the numerical class of A will be trivial. So consequence, so this is for any polarization. So the determinant of A is numerically trivial to 0, and the determinant of Q by the same line of argument is also numerically trivial to 0. And as I pointed out in the beginning with this Kawamata result, that means I can just as well assume that these sheaves are 0. Because this Miyaoka argument works with any polarization. If you have a polarization for which the slope is positive, then Miyaoka gives you rational curves which you know don't exist. If it's negative, then it's not destabilizing, because Tx has, or omega 1x has slope 0. No, the Kx is linearly equivalent to 0 at this point. So its slope is 0 with respect to any polarization. The trivial sheaf has always 0 slope, no matter what polarization. Yeah. Yeah, that is true. Maybe we discuss that later. Would be, thanks. Right. So I can assume I can assume that determinant A is OX. In particular, that means I have a P form where P is the rank of A. So have the determinant gives me a P form. P is the rank of A. And when I have a P form, I get a complementary n minus P form. That we have seen in step 2. Get a complementary n minus P form. And now, as a matter of linear algebra, using all the numerically trivial sheaves here, by linear algebra, you can show that we get a complementary sheaf B such that A plus B is the same as omega 1x. So I'm not going into the details. That needs, of course, to be shown. But the basic outline of ideas is first you show there's some duality in the ring of differential forms. Assuming that you have instability, you get a form. The form has a complementary form, so you get a complementary sheaf. And you do this as often as you can, perhaps going to more and more covers, because you will frequently need to assume that something that's numerically trivial is actually trivial. And once you have the decomposition that has the most summons among all decompositions, then there's no further instability anymore. And so you get the decomposition as we formulated in the theorem. Also, if these summons that you have here, if these were not stable with respect to Lie bracket, then again you find a decomposition in a similar way. Then the O'Neill tensor gives you destabilizing subsheaves in the other summons, which you can then use to decompose further. So this is essentially the line of argument. I would leave it there and maybe recall that this is essentially an idea of Bogomolov. And our contribution is that we took Bogomolov and beamed him into the 21st century. So space-age Bogomolov, if you wish. I should also say that there's related work that has appeared recently by Henri Guénancia, who used analytic methods to come up with related results, proving that in our setting, the tangent sheaf is polystable. So some of this, or much of this nowadays, can also be retrieved by, I would say, hardcore analysis. So let me just write this down. Related results by Guénancia. Right. So this is what I would like to say about the decomposition. Many details pending, of course. But I think it's much more worthwhile, because nobody will remember any details, if I turn my attention now to a different method. So far, we have used differential forms on singular spaces in order to discuss our varieties. There's another technique here, and this pertains to the fundamental group. So let me now open a new chapter and say something that we know about the fundamental group that allows us in a different way to attack our varieties with vanishing first term class. So this is paragraph 6 then. fundamental groups. The question that I have is this. So as before, setting is X a now quasi-projective. I don't need compactness anymore. Quasi-projective, say, KLT variety. Then I have X, and I have its smooth locus. And I have the inclusion map. What I would like to discuss now is fundamental groups. So I have a map between the fundamental groups, which comes from the inclusion. And it's an old result. I think the canonical reference is an old paper of Fulton-Lazarsfeld that under basically no assumptions, such a map will always be surjective. I like to understand the kernel. And because I'm an algebraic geometer, I would really go to the profinite completion of the fundamental group and discuss the algebraic fundamental group. So in particular, I'm asking the question, is it true? Ideally, I would like this to be an isomorphism. Is it true that any étale cover of the smooth locus extends to an étale cover of the whole space? I know this is, I think, Zariski's main theorem in the form of Grothendieck, that I can always close it up to a normal variety, but it's not clear whether that normal variety will be étale over all of X. Maybe, maybe not. And I like to understand this. That has been done in the case when X has isolated singularities. There, it's a result of Shengyang Xu that the algebraic local fundamental group of an isolated KLT singularity is always finite. And this uses pretty much everything which is known in minimal model theory, I believe. Would you agree to this? Almost. He doesn't shake his head violently. Yeah. So in the general setting, of course, you don't have isolated singularities, and then it comes down to construct a Whitney stratification in an appropriate manner, then inductive proofs by cutting down, and blah, 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 blah. So the result then is we can't exactly say. Ideally, I would say this map here has finite kernel. This is not true. What we can say is theorem in this setting. This is again Greb and Peternel. So what we can say is given a, say, tower of quasi étale morphisms, say X is X0, X1, X2, and so on, such that any of the Xi is Galois over X, such that all Xi are Galois over X, then almost all arrows are étale. So they don't branch anymore. In particular, that does not show, we mistakenly thought for a while that would show finiteness of the kernel here. This is wrong. But it does show that when you have a KLT space, you ask yourself, is there a cover of the smooth locus that does not extend as an étale cover of all of X? Okay, then you go there. Then you do the same trick again. Is there a cover, étale cover of the smooth locus, which does not extend to an étale cover of all of X? Yeah, then you take this and you build a tower like this. And what this result says is there's no infinite tower like this. After a while, there's no quasi-étale cover anymore. Your covers will all have to become étale. So that means, corollary, X as above, there exists a quasi-étale cover, say X twiddle over X, such that the algebraic fundamental group of X twiddle reg, the smooth locus, and the algebraic fundamental group of X twiddle are isomorphic. So in a sense, this could be called a maximal quasi-étale cover because afterwards there's nothing quasi-étale anymore. Any cover that's étale on the smooth locus will be étale. Interestingly, as a side remark to the experts, whenever I see such a result, I would like to choose X twiddle in some minimal, maximal, unique way. We know for a fact by examples this is not possible. This seems to be, to me, that looks like a meaningful statement, but yet I don't know what it means. So examples show that, so we can prove that there is in general no way, no canonical way to choose X twiddle. So what can you do with this? So what application do we have in mind? There's a couple of applications that I have in mind, but for now let me concentrate on one, and that pertains to the notion of flat sheaf. Not flat as in the sense of tensor product is exact, but flat in the sense of differential geometry. A sheaf is flat, so a sheaf on an analytic space is flat if it's induced by a representation of the fundamental. So, so this is paragraph 7, applications to flatness. So again, as before, X a KLT space. So, and then say F flat sheaf on, I would like to say the smooth locus, but let me be very precise here. Flat sheaves, this is something that exists in the analytic world because I'm talking about representations of the fundamental group. So this is a coherent sheaf on the associated analytic space. Then if I have a coherent sheaf on the associated analytic space, I would like to make this a coherent sheaf on X, which in algebraic geometry is very simple, and in complex geometry is usually very, very hard. So in that particular case, for flat sheaves, Deligne has done for this for us. Deligne has shown F extends to a coherent sheaf on X, I mean the analytic space. In particular, if X is projective, that means our sheaf that we started with, which initially was an object of complex geometry and not algebraic geometry, is really algebraic. So in particular, if X is projective, that means F is algebraic, which is not obvious from the outset. Now, what we can contribute to this is the observation that the extension, let me call this F bar maybe, the extension, is again a flat sheaf. Now, how do we prove this? Is a flat sheaf after going to a quasi-étale cover like this. So the observation, if pi1 of x reg is pi1 of x, then f is again flat, in particular locally free. How do we prove this? So if I'm allowed to forget that we're talking about profinite completions here, this is a no-brainer. If I had this result for fundamental groups instead of algebraic fundamental groups, then what is a sheaf? A sheaf is a representation of the fundamental group. Now, if the two fundamental groups are the same, then extending the sheaf is a no-brainer, because I need to extend a representation from something to something that's isomorphic to it. That is, of course, very easy. However, we don't have that. What we are having is we have a representation of the fundamental group, but we have only a statement about algebraic fundamental groups being equal. And now I need to think what I can do in this case. So let's see. So proof is, we know f comes from a representation, say, rho pi1 of x reg the analytic space to some GL. And let's call the image, I don't know, R. Let R be the image. So then what do we have? We have, in the middle, there's pi1 of x reg, the analytic space. I have the morphism to R, which is a subset of some GL. And so this is the morphism rho. And I have the inclusion map, which goes to x. And then I have the same thing again on the level of profinite completions. So here I have the algebraic fundamental group. So P1 of x reg n, I can write it like this, goes to P1 of x. So this is surjective by Fulton-Lazarsfeld. Then profinite completion is a right exact functor. So this will again be surjective. Oh, this will be isomorphic. Very good. I have the profinite completion maps here and the profinite completion of my representation map. Now, how does that help me? I have a representation here, and I would like to extend it to a representation here. So how can I find a representation here? Well, there's two things. First, I know that our spaces are triangulizable. That means fundamental groups are finitely generated. So here we're discussing finitely generated matrix groups. And by Maltsev's theorem, these are residually finite. In particular, Maltsev proves that the profinite completion map is injective. So I want to define something here. I can go up here. This is an isomorphism, so I can continue here. And I can continue here. However, I know this map is surjective. So any element that I hit really comes from down here. And this arrow is injective. So that means R is identified with its image in our hat. And we end up in the image for this being surjective. So this I call, I don't know, alpha. So observe that the image of the map pi1 of x goes to image of the map pi1 of x goes to r hat is in the image of r to r hat, which is isomorphic to R for that morphism alpha being injective. So in particular, I can continue down here. And that gives me a representation of the fundamental group of X, starting from a representation of the fundamental group of the smooth locus. And being able to extend my representation means I'm able to extend my flat sheaf. So consequence is for the spaces that have the singularities of minimal model theory, we can improve on the linear as a result. So X with KLT singularities, then F, a flat sheaf on X rec, and then the associated analytic space, then there exists a quasi-étal cover X twiddle such that pullback of F, pullback of flat is flat, while extends to a flat sheaf on all of X twiddle and the associated analytic space. So this is extremely useful for what it tells you at the end. This is an informal consequence. I can make this a precise statement if somebody wishes, but maybe I should spare you the details. What that essentially means by the end of the day is that pretty much any criterion that you know for flatness, so we are thinking of Donaldson, Simpson, Ciobando type flatness criteria, for spaces with KLT singularities, it just works. So consequence, so flatness criteria, all, this is not very precise, but I hope you forgive me, they all work on KLT spaces. So for instance, example, if you have X projective and terminal, I will say a word about the KLT space later, and you have F, a stable sheaf, so I should say an H stable sheaf, H an ample polarization, such that C1 of F times H to the n minus 1 is 0, and C2 of F times H to the n minus 2 is 0, then the sheaf is flat, in particular locally free. In particular, So this is our variant on singular spaces of the flatness criterion of Simpson. Special case, F could be the tangent sheaf. Then this tells us, if we have the tangent sheaf with vanishing first and second Schoen class, this tells us that the tangent sheaf is flat. In particular, it's locally free. And we have seen this was this Zariski-Lippmann business from the first lecture this morning. If the tangent sheaf is locally free, that means the space is smooth. So in particular, we can see that if I have a space where the tangent sheaf has these properties, it has only quotient singularities, because we go to quasi-étale cover, we argue there. And of course, many of you will know the classical result from differential geometry that if you have a manifold, a projective manifold, with a flat tangent sheaf, this is a quotient of a torus. So in particular, the classical characterization of torus quotient that you have seen, I don't know, in Kobayashi's book maybe, for KLT spaces or terminal spaces, it just works. For KLT spaces, there's an additional twist to the subject because the terminal singularities are, terminal spaces are smooth in codimension 2. That makes it easy to define C2. If I have a KLT space, then in codimension 2, that will have quotient singularities, and then I need to use OR before Chern classes, and everything will work just the same. So this is one application that I have in mind to the classification or structure theory, if you would like to use great words, for varieties with vanishing first Chern class, and then hopefully for all varieties with codimension dimension 0. There's more to this. We're currently working on further generalizations. It seems, I'm pretty optimistic, that much of the work of Carlos Simpson, like his non-abelian Hodge theory, his methods to construct variations of Hodge structures in spaces that are initially not the base of a family or something, and his characterizations of bounded symmetric domains and quotients there, that has a chance to work at least to some extent for spaces where the singularities of minimum